Hi there, this video is to demonstrate the process of fake factoring, which is a way of factoring a quadratic with an a value that doesn't equal 1, and it's an alternative to factoring quadratics by grouping, which can be a little bit confusing, especially if you're first learning how to factor. So fake factoring is a way of factoring a quadratic like ax squared plus bx plus c if the a value doesn't equal the number 1. If it's any other number than 1 and the quadratic can be factored, then we can use this method of fake factoring. And it has 3 steps that are different from factoring a quadratic with an a factor that is 1. We know that we can use a t-chart and a list of factors that multiply to c and add to b if we're factoring a quadratic. And this relies on the same premise, but the steps that are going to be a little bit different is first, instead of just finding the factors that multiply to c, we're going to multiply a times c first. So I like to draw this arrow to show that multiplication. We're going to start by multiplying a times c, and that's the factors that we're going to find that multiply together to get the number a times c. They do still have to add to b. That part hasn't changed. Once we find the factors that multiply to ac and add to b, we're going to move on to the next step, which is writing those factors inside our parentheses. But we're going to change that step a little bit as well. So after we multiply a by c and find those factors, we are going to put ax in both sets of parentheses. And this is why it's called fake factoring, because technically this step is very wrong. It won't give us the right answer if this is all we do. So we will have to put ax in both sets of parentheses. So if this equation up here is 4x squared, then we would put 4x in both sets of parentheses. And we'll see some examples to explain that. The last step is to go ahead and take care of the problem that putting ax in both parentheses creates. When I put ax in both sets of parentheses, I'm making a quadratic that is a times larger than what I actually want. It's a times too big. So the last step is going to go ahead to b to divide that a back out. So if it's a times too big, so for example that a value is 4 and it was 4 times too big, we'd have to divide 4 back out. And I want to go ahead and illustrate this with some examples. The first example I want to do, we'll call it example A. Example A is going to have the quadratic 2x squared minus 11x plus 15, which we can see has no greatest common factor to take out, and the a value, 2, is obviously not the number 1, so we can't use traditional factoring. So we're going to go ahead and use fake factoring. So we're going to start by multiplying a by c, 2 times 15. That gives us the number 30, and this is going to be the number we're going to use in our t-chart. We need 2 numbers that multiply to 30, that add to the same b value we're used to. They still have to add to this negative 11. So if you're unfamiliar with using a t-chart, we're going to go ahead and look at the factors of 30. We can make a list of them. 1 times 30, 2 times 15, 3 times 10, and 5 times 6. And if I continue with my factors, I'm going to end up repeating myself because the next factor would be the number 6, and I've already got it. And then I would look at these factors side by side and try to determine which ones could combine to give me a negative 11. Now, since my 30 is positive, my factors all have to be the same sign. They either both have to be positive or both have to be negative, and they would add to an 11. So if I check here, 1 and 30 would add to 31, 2 and 15 would add to 17, 3 and 10 would add to 13, but 5 and 6 would add to 11. If I want them to be a negative 11, however, they're going to have to be a negative 5 and a negative 6. They would still multiply to a positive 30, but they would combine by addition to a negative 11. So I found the factors that I'm going to put in my parentheses, which is where I change the way that I write my parentheses. Instead of just putting x inside each factor, we're going to put ax inside this factor, even though it is technically wrong at this point. So 2x inside both, and then the negative 5 and the negative 6 that we just found by factoring. Now, at this point, if this is my final factor, and I tried to FOIL this back together, I would end up with 2x times 2x, which is 4x squared, and I only want 2x squared. This is 2 times too big. This is where I have to do my last step. Oh, I had a typo here. I'm sorry. This was supposed to be minus 6, because it was this number here. All right. This is where I have to do my last step and take that extra 2 back out. This is 2 times too big. I have to divide by 2. Now, because both of these factors are being multiplied together in my numerator, it doesn't matter which one of them I divide by 2, I'm still going to have reduced my total value by 2. So I can divide the one where it goes evenly. So if I want to divide one of these by 2, I'm going to go ahead and divide this side by 2 because both of the numbers inside are divisible by 2 evenly. So if I go ahead and divide that by 2, the left side will stay the same. 2x minus 5 won't change. But on the right side, I'll take 2x divided by 2, that's just x. Negative 6 divided by 2, that's negative 3. Once I've done this last step of dividing a back out, this is now my final answer. It does multiply back together to give me my original function, which is what factors should do. So if I check my work here, I can do 2x times x, I would get 2x squared. And then I could do 2x times negative 3 and negative 5 times x. If I do that, 2x times negative 3 is negative 6x. And the inside here, negative 5x gives me another negative 5x. So altogether, I would have negative 11x, just like I wanted. And then the negative 5 times negative 3 would give me the positive 15 I needed. So these guys here are my final factors. So 2x minus 5 times x minus 3. And I found them by doing some steps wrong in the middle, but then fixing my errors by dividing a back out, and I have my final solution there. Let's go ahead and take a look at another example. We'll call this example B. In example B, we're going to have 12x squared plus 13x minus 4. Again, I don't have a GCF. I can't reduce anything, and my a value, 12, is obviously not 1. So we're going to start by multiplying a by c. 12 times negative 4 gives me negative 48. That's going to be the value in my t-chart that I'm going to have to multiply to, and my terms are going to have to add to my original positive 13. So we can go ahead and list the factors of 48 here. 1 and 48, 2 and 24, 3 and 16, 4 and 12, and 6 and 8. And that's as far as I can go without repeating myself. And now again, these are going to have to combine to 13, but because the 13 is positive and this 48 is negative, the negative 48 means that these factors are going to have to be opposite signs, and they're going to have to be 13 spaces apart essentially. So 1 and 48 are only 47 spaces apart, 2 and 24 are 22 spaces apart, 3 and 16 are 13 spaces apart. And if I want them to combine to a positive 13, I need a positive 16 and a negative 3. So those are the numbers that are going to go inside my factors. And again, my factors have that extra step. Instead of just putting x in both sets, I'll do ax, which in this case is 12x, and then those two numbers that I found, positive 16 and negative 3. Now this factor, this group of factors is now 12 times too big. If I tried to FOIL this back together, 12x times 12x is 144x squared. I only want 12x squared. So it's 12 times too big. I have to divide 12 back out. And this is where something interesting happens, because if we take a look at the numbers inside our parentheses, they don't divide by 12 evenly. And I don't want to have factors that have fractions in them, because let's be honest, who likes fractions anyway? So I'd rather divide this in a way where I don't have to get fractions as a result. And the way I can do that is by knowing that I have to take out a total of 12, but I don't have to divide it out all in one step. If my number is too big to divide out all in once, I can break my 12 into pieces, and those pieces are called factors. I have to divide out a total of 12, and I can do that by dividing out the factors of 12. In this case, my factors of 12 are 1 and 12, 2 and 6, and 3 and 4. And if I divide by both of these numbers at a time, one of these sets of numbers, I'll be able to take a total of 12 out, but hopefully get even results instead of fractions. Now, I already looked at trying to divide one of these by 12, and it won't work, so we're not going to use those factors. I can divide this group over here by 2, but neither of these sets of factors can be divided by 6, so that won't help. But if you'll notice here, I can divide one of these by 3, and one of them by 4, which is a total of dividing by 12, but the 3 and 4 go into these factors evenly. So as long as I'm taking out a total of 12, I'm good to go. So on the left here, we're going to divide 12x plus 16 by 4, and the result will be 3x plus 4. That's been divided by 4. Now all I have to do is divide the right side by 3, and I'll have taken a total of 12 out. So on the right side, 12x divided by 3 is 4x, and negative 3 divided by 3 is negative 1. Now this is my final factored form, and we can check our work to make sure it'll FOIL back to where we started. 3x times 4x is 12x squared. 3x times negative 1 is negative 3x. 4 times 4x is positive 16x. If we add those together, we get 13x. And finally, positive 4 times negative 1 is negative 4. So we've ended up right back where we started. So this is the factored form, and we used fake factoring to get it. My very last example is going to show you that even if we don't have a trinomial, even if we know maybe in the back of our heads that a quadratic could be factored another way, for example, in this last example C, I'm going to look at 4x squared minus 9. This is technically a difference of squares, and if you learn the difference of squares pattern, you don't have to use this long form of factoring at all. But if you can't remember the pattern for difference of squares, you can still find the factors of an equation like this using fake factoring. And the first thing you have to do is write it out in standard form with a placeholder for the missing x value. So we have x squared, and we have our constant at the end, but we skipped the x to the first power in between them. So I would rewrite this 4x squared and 0x, and then the negative 9. So we have no x's in between these terms. And that's helpful for filling in our t-chart, because what we would have to do for fake factoring is multiply a by c, 4 times negative 9, which is negative 36, and that would go into our chart, and it would have to add to the b value, which in this case is 0. And we can find the factors by finding the factors of 36, 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6 and 6. Now we have a negative 36, which means our factors have to be opposite signs, and the two numbers, which are opposite signs that add to 0, would be 6 and 6. We have a negative 6 and a positive 6, and those would add to 0 and multiply to negative 36. So those would go inside my factored form, and again I would put ax in both factors, 4x in both factors. One of them would get the positive 6, and one would get the negative 6. And this is where we would say, all right, we're almost done, but this is 4 times too big. I have to divide 4 back out. Just like our last example, 4 is too big to take out all at once. My 6's here are not divisible by 4 evenly, and I don't want fractions. So instead of taking 4 out all at once, what I can do is break 4 up into its factors, 2 times 2, and I can divide each one of these by one of the 2's. Altogether, I will have taken 4 out, just in smaller pieces. So 4x plus 6, if I divide that by 2, I get 2x plus 3. And if I divide the second factor by 2, I get 2x minus 3, which, if you know the difference of squares shortcut, is the exact same thing you get factoring this using that rule. So 2x plus 3 times 2x minus 3 would be our final answer using fake factoring.